Well, good afternoon. It's about 3:41. Sorry we're late getting started, but I had an instructor in my office who was asking a bunch of questions. We're trying to work through some issues, and the time slipped right on by, so sorry about that. But I'm still the only one in the room, even though I'm 11 minutes late getting started. So anyway, we are in Chapter 4, higher order differential equations, in Section 4.1, Preliminary Theory, Linear Equations, and we're at the bottom of page 120, Example 3, on boundary value problems. And the issue here is boundary value problems can have many, one, or no solutions, okay? And they go back to example 9 of section 1.1 a long time ago. It said we saw a two-parameter family of solutions of the differential equation. And let me get my pen set up. Okay. X double prime plus 16x is equal to 0. Okay. And that the two-parameter solution was x is equal to c1 cosine 4t plus c2 sine 4t. Okay? That was the solution, two-parameter solution. Okay? Now, that's the setup. Suppose we now wish to determine the solution of the equation that further satisfies the boundary conditions, and here's the boundary condition. Actually, it should go up here with the top one. The differential equation, x of 0 is equal to 0. That looks like it could be very legitimately an initial condition, but the boundary condition, x of pi halves, is also equal to 0. Now, the deal here is, if that would have been x prime at 0, that would have been an initial condition. But this is at two different locations, so this is a boundary condition. Just like we talked about one of the 4 cases or so that we talked about at the end of class last time. Okay? I'm so sorry. Now, the first of these, if you plug x equals 0, now, t is equal to 0. The independent variable here is t. T is equal to 0 into this. You get x is equal to c1 times the cosine of cosine of 0, because 4 times 0 is still 0, plus c2 times the sine of 0. That's not a theta, it's a 0. Okay. And we say that's equal to 0. Well, we know that sine of 0 is 0 already, so that term's out of there, not contributing anything. And cosine, though, is equal to 1, so this says that C1 has to equal 0. So now we're down to a one-parameter case, and if we go to the second boundary condition here, and we see that x equal C1 is 0. So C2 times the sine of 4 times pi halves, well, that will be 2 pi, and that this is equal to 0. Hey, we don't know what c is because sine of 2 pi is equal to 0 itself. So no matter what c is, that is still 0. So we don't have a fixed solution, okay? Observe that the first condition gives you c1 0, so x equals c2 times the sine of 4t, but when you put pi halves in there, it's satisfied by any choice of c since sine of 2 pi is 0. So it's the boundary value problem with those boundary values has infinitely many solutions. The figure at 412 shows just a few of those. Basically, any sine curve with that C is a anywhere from 1/4, 1/2, minus 1/2, I'm pretty sure minus 1/4, 0, 1, I think 2, 3, I think all of those would give you solutions, okay? And so there's infinitely many solutions. Now, what if you change the second boundary? Let's see. Kept the first one the same, made the second one x of pi eighths is equal to 0. Okay? Now, you plug in, you still get C1 is equal to 0 from the first one. Okay? So then you have x equal C2 times the sine of, when you put pi eighths, 4 times pi eighths is pi halves, and that equals 0. Well, sine of pi halves is 1, so this says that C2 has to equal 0. Well, guess what? You don't have a very interesting problem at all. X equals 0, that's the flat line. There's no other solution. X equals 0, okay? There is no other, okay? And by applying that, you get that demands that C2, x equals 0 is the solution, the one and only solution to the problem, okay? There are no others. X equals 0 is it. Okay, now, I need to do the third part, C part. Try to do that off to the right a little bit here. Finally, if we change the problem to the differential equation is the same, the first boundary value is the same, but the second boundary value is this. X of pi halves is equal to 1. Okay. If we do that, of course, that first condition still makes C1 equal 0. But now when we plug into the remaining equation, x equal C2 times the sine of t equal pi halves, 4 times pi halves is 2 pi, so that would be 2 pi, and you have that equal to 1. Guess what? This thing is still 0. And you have 0 is equal to 1. That's impossible. There are no solutions to that. Absolutely none. Okay? It can't happen. Because C2, no matter what value you take on, it can't meet that second boundary condition. Okay? So, boundary value problems could have issues with them. Infinitely many solutions, no solutions, or one and only one solution, which is usually a pretty good case. In this case, it just happened to be 0 was the only one. Now, it doesn't always turn out that way. You may have one that's exactly one solution that makes sense. Okay? Now, let's move on to 4.1.2, which is, have we not seen this before? Homogeneous or homogeneous equations. Okay? Now, just a flashback here. It's written in the text here. The word homogeneous in this context does not refer to coefficients that are homogeneous functions. Okay? This whole differential equation is a homogeneous, okay, or your series of them, you know. So it's different from the earlier in section 2.5 when we referred to the coefficient equations, or coefficient expressions that had to be homogeneous functions. In other words, all having the same powers, okay. This is not talking about the same thing. These are homogeneous, meaning they're all alike in some sense. So here's a linear nth order differential equation of this form. Seen this before. A sub n is a function of x times the nth derivative, and we're going back to y's here, dx to the n, plus a sub n minus 1 of x times the n minus first derivative of y with respect to x, to the n minus 1, plus a sub n minus 2 as a function of x times the n minus second sorry derivative of y with respect to x to the n minus second, plus dot 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 all the way up to until you start coming down to a sub 2 of x d2 y dx squared plus a sub 1 of x dy dx plus a sub 0 of x times y. If that's equal to 0, that's what we call a homogeneous equation. All right, good deal. Okay, thanks. Turn on the light switch this way. Good deal. A little more light to do. Thank you. And I just marked you present. Okay. All right.
I hated to leave Monday, but I just couldn't get away Monday.
Yeah. All right, let's see. Monday was all absence day. I just talked to the empty room.
I know how much you enjoyed it.
Oh, yes. Yeah. So.
All right, we're in 3.
No, 4:1.
Four.
Chapter 3, we're not doing. It's modeling, and I don't do modeling. Okay. Never.
Yeah, I'm not big. I don't have a body.
Okay. All right. I just finished example 3 at the bottom of page 120, at the top of page 121, talking about boundary value problems, which was the last thing we did Monday, or I did Monday in here by myself. But a problem with boundary value problems as opposed to initial value problems is that sometimes they lead to infinitely many solutions, sometimes one solution, and sometimes no solutions. And that example gave examples of each of those. And even the one solution was a trivial solution, so it wasn't a very interesting solution itself. Now we're moving into 4.1.2, and if it sounds like a familiar topic, it means something different here. It's homogeneous or homogeneous equations, okay? And what we mean by this is it's a linear nth order differential equation, which means all the coefficients of your various derivatives here and the function itself are functions of x alone. No y's in these. And no derivative is raised to any power, and no derivative is multiplied by any other derivative or the function itself. Okay? That makes it linear. Okay? And
what was the second part you said?
Okay. First part was all the coefficient functions are functions of x alone. No y's in the coefficients anywhere. Even of the constant term here. Not constant term, the function y, okay? The zeroth derivative, in other words, the function itself, okay? And the second part, okay, is that all of the derivatives are to the first power only. They may be derivative, but they're only to the first power. You're not having any of these squares or cubes or to the 1/2 power or anything else like that. And then the third thing is that you don't have any products of derivatives or y's. In other words, you don't have a third derivative multiplied by a first derivative, or a second derivative multiplied by a fifth derivative, or a first derivative multiplied by y. You can't have any of those. The only place y shows up is in a single derivative not raised to any power, okay, in every term, okay. Now, if that's your linear higher order differential equation, if that's equal to 0, we call it a homogeneous or homogeneous linear higher order differential equation of the nth power, nth degree. Now, if this equal sign over here is followed by a g of x, then this is called non-homogeneous. So this one's homogeneous or homogeneous. I don't know how they actually pronounce it. And this is non-homogeneous or non-homogeneous. Okay, if that was milk, that would be homogenized, but I don't know if this is milk or not. Okay, so if it's equal to 0, it's homogeneous or homogeneous. If it's not equal to 0, equal to some function of x. Now again, no y's there either. Functions of x, then it's a non-homogeneous linear nth order differential equation. Okay, got all the pieces there. Now, as they say in your text, then the next to last line in that first paragraph, big old long paragraph in 4.1.2, the word homogeneous or homogeneous in this context does not refer to coefficients that are homogeneous functions. Okay, if you remember back for that in 2.5, then they had coefficient functions, and you could have x's and y's in them together then. But if this, the total degree of your exponents in this, if that was 5, and this term was 5, and that term was 5, then that's what we called homogeneous then. They were homogeneous functions as your coefficient functions. That's not what we're talking about here. This is equal 0 or not equal 0. That's other meaning of homogeneous or homogeneous, okay? So they do make that distinction, which is enough to drive you crazy, but yeah. We also see that to solve and by the way, your test, that you got a copy of the test, didn't you? Those homogeneous are the chapter 2 homogeneous, not these. Okay, all right. All right. We shall see that to solve a non-homogeneous linear equation, 7, you must first solve the associated homogeneous solution equation. So that's why they're making a distinction. If you have a linear nth order ordinary differential equation that has a g of x here, the first step is to make the g of x 0. Solve that. And then once you solve that, go back to deal with the g of x. Okay. So what we're going to start with now is not having the g of x, just how do you solve that when it's equal to 0, when it is homogeneous, your homogeneous solution. So that's what we're going to look at in 4.1.2. Okay. Now, here are some of the assumptions. The coefficient functions, the a sub i's here, a sub n, a sub n minus 1, a sub n minus 2, all the way down to a sub 2, a sub 1, and a sub 0. Okay? And the g, once we have a g in there as well, those are all continuous functions. All continuous functions. Okay? That's the first one. The second condition, or this one, assumption. Okay? The a sub n, that first one, is not 0. Now, the others could be 0. That's no problem for them to be 0. The reason this one can't be 0, our statement is this is an nth order differential equation, linear differential equation. If a sub n is 0, that whole term's 0, and then it's an n minus first order differential equation. So for it to be an nth order nth order, a sub n can't be 0. Okay. So that is a sort of a non-starter, you know, sort of a duh. Okay, you can't have that one equal 0. So, of all things, let's just introduce a new operator, okay? In calculus, differentiation is often denoted by the capital letter D. And I'm not too sure why there. We already have these D's, little d's, you know, written in this form. We also have our prime notation, and when you exceed 3, you go to things in parentheses, you know, and that indicates differentiation. So why not have another way to indicate differentiation, and that's the letter capital D. Okay? And what the capital D stands for is this. dy is dy dx. Okay? So in other words, the capital D is equivalent to, I'll put a 3 thing there, d by dx. If you have a D, it's a d by dx. Okay? So it's just a shorthand of not having to write d by dx, you write capital D. Okay? And it's called the differential operator because it transforms the differential function into another function. Sort of. Okay? You know, your differentiable function, y, is changed into its derivative, or whatever derivative. Now, here's a little catch here, and it's a pretty clever little catch. What would d2 represent? It looks like it's d squared, but remember this is an operator, and you don't square operators. Well, that would be d2 by dx squared. And d superscript 3 would be d cubed dx cubed. And d to the n would be d to the n over dx n. Okay? Now, if you'll notice, if you just take and put a y in here, yeah, that gives you exactly the same thing. If you put a y in here, that gives you exactly this one. Okay? d2y dx squared. The cube we didn't have here, d to the n, that's this one. dny dx n. So yeah, it's just a shorthand for whatever. The superscript is the order of differentiation. Okay? Is that the right way to say it? Is a derivative. It's which derivative you're talking about. Which I think, because we're using order in a different way, I probably shouldn't use that one. Okay. So, another way to look at this, it's d of dy. Okay. If I put a y here and a y here, okay, that would be the same one up there. Then this would be d of dy, which is d by dx of dy dx, which is d2y dx squared. Okay? Just like it was before. I mean, there's nothing new here. It's just a different way of stating it. Okay? Now, here's one kind of reason they do it. Okay? Then they can refer to something like this as an a sub n, that's a function of x, get out of there, d n y plus a sub n minus 1, function of x, d to the n minus 1 of y, plus, you know, number one, you're shortening how you have to write, a lot less to write, but then what it turns out being, it looks like, especially if you kind of don't pay too much attention to the a sub x is there, it looks like you wind up with a polynomial function in D. Where those aren't really squares or cubes or anything else, but it looks like that. And then when you go to solve the things, you can factor them and treat them just as if they were polynomials. So that's the other advantage of it, where it's not so obvious with the d by dx's, but when you have the d's like this, yeah, you can sort of treat them as if they're polynomials. Polynomial expressions involving d, such as, I'm going to go to a clean page here. Is that okay?
All this is really teaching us
is what?
All this is really teaching us is another form of substitution.
Kind of, yeah. And in fact, once we get to doing it, it even looks more like that. It really does. So that's a good way to look at it. So you can have a d plus 3. Okay, if d plus 3 is operating on y, what does that mean? It's d by dy dx, that's your d part, plus 3y. See, the y goes in the d by dx, and the y follows the 3. Okay? Or you could have a d2 plus 3d minus 4. Okay? And that would simply be, or I don't know how simple it would be, d2y dx squared plus 3 dy dx minus 4y. Okay? So you can just write your differential equation in a lot simpler form. You just do that like that. It's just a lot easier to write, and then suggest that you can factor or do other things that you could with polynomials. Okay? Now, so far I've been leaving off the a sub x's here. They can be in there too, like 5x3 d cubed minus 6x squared d squared plus 4x d plus 9. I can't write. Okay. Those are also differential operators. It's just that this is your a sub x, a sub 3 of x. There's your a sub 2 of x. Now, I kind of hate it that they made the powers of the coefficients exactly the same as the power of d. It's not required, okay? It's not required for them to be that way, but their example was just that way, okay? Sorry about that. But those are all also differential operators. In general, we define an nth order differential operator of a polynomial or a polynomial operator to be, it just seems like to me they keep coming up with different things just to add another level of complexity to it, where we're really not going to use it that much. Yeah, what were you going to say?
This doesn't look anything like a polynomial.
What's that?
What they're giving us here,
yeah.
Is L equals.
Yeah.
Yeah, that doesn't look anything like a polynomial to me.
Right.
I would never pick that out. But.
Yeah, except that and what do they call it? Just L. Okay. Here's a new operator, another operator. Okay, and this one's called a linear operator. And this one would be a sub n of x. That would just be like your 5x cubed in the one above it. D sub n, d to the n, plus a sub n minus 1 of x. But, okay, now wait. If you remember back when they were talking about polynomials, now I'm trying to relate to what you just said. When they were talking about polynomial functions, they would have a sub n, x to the n, plus a sub n minus 1, x, where these were just coefficients, numbers. Didn't have to be real numbers. I mean, they had to be real numbers. Didn't have to be integers. They could be fractions, decimal, positive, negative, rational, irrational, any kind of number. Okay, so you call them that. Now with a differential equation, those coefficients are now functions of x. So it is one level of complexity greater, but it's still the same kind of concept. There's no y's in those x's, just like there's no x's in the a's that you do at a x to the nth. Okay, a sub n x to the n. That's just a number. Well, now you're doing a to the nth of x times d by dx of y. Well, that only contains the y's there, you know, sort of, you know, but you don't have any x's mixed in with the y's there. Okay. So anyway, d to the n minus 1. Let me see how far they're going to take this. Well, I usually do more than that, but they don't. D, I guess, to the first y plus, well, they didn't put the y's in, did they? Yeah, they're leaving them out. Sorry. Oh, I left off my coefficient too. Let me erase all that. Okay, sorry. I knew I was missing something here. A sub 1 d sub 1. This is a of x. A sub 1 of x. That's what I mean to say. D plus a sub 0 of x, and that would just be the y, and that's equal to, well, they're not putting any, it's equal to anything. That's just the operator that now combines the d's with the a's, okay? Whereas up here, there were no x's listed here. You could include functions of x's, and now you just do those as, you know, the corresponding thing. They're only functions of x's times your d's there. So that's then called your L operator, okay, which is the most generic form of your differential equation operator. Not that we're going to use this that much, but that's the differential operator, and they also call it a polynomial operator because it is operating on those d's, which d was called the differential operator too. So I haven't figured out why they feel like it's necessary to do it. It's easier to me to just deal with the functions as they come up and don't mess with all these operators. But I know that's probably not true. And here is an example of that. So what if we are operating with L onto an alpha, which is some constant, alpha of x plus beta g of x. Oh well, there's no parentheses in the front here, sorry. Got carried away with my parentheses and close that off. Now why they didn't put bright brackets there, I don't know. That this is alpha L of alpha of x plus beta L of g of x. Okay? L possesses this linearity property that this is true. That L we just put up there is called a linear operator. That's what I kept wanting to say, but they were still calling it the other, because this kind of a statement is true. You can basically, L operating on a sum, you can break it up into the sum of the L's operating. That's what we did there. But the constant multiplied by a function, L operating on that, or the constant on the outside, in both of those, and you have that. So that combination of the two, the distributing over a sum and pulling out the constants, that makes it a linear operator. Okay. If you do linear algebra ever, you'll see that out of your ears. All right. Why bring all this up? I'm not sure, but here's what all they seem to do with it. Now, probably not all, but it seems to be. Then when they say L of y is equal to 0, the L of y incorporates all the other stuff, okay? And then the second one, that's your homogeneous linear first order differential equation, no, nth order differential equation, and here's your non-homogeneous. L operating on y is equal to some g of x. Okay? Okay. Yeah. I think I skipped something there. I'll probably write this again, but I do need to say the other first. Sorry, I should have just erased the whole screen, but it's the same difference. Okay, I sort of skipped this. Any linear differential equation can be expressed in terms of the D notation, and then they turn it around and do the L2, but they talk about D notation here. So if this was your thing, yuck. Okay, sometimes it loses its mind here, and I'll lose mine. Okay, here is a y double prime plus 5y prime plus 6y is equal to 5x minus 3. There's a differential equation, right? Now, right now we don't know if there's boundary conditions or if we're going to do a general case or whatever. Okay, probably general. Okay. Now, that can be written as the y double prime becomes d2y plus 5dy plus 6y is equal to, and to the right, yeah, 5x minus 3. Okay? To me, that's no shorter. That's actually a little longer, but, you know, it's okay. Perfectly fine. Or you can then kind of factor out the y, and you just have d squared plus 5d plus 6 times y is equal to 5x minus 3. Okay? And again, it's just playing around with the representation. Then if you go up and use your L operator, okay, which I don't know why, you can write the linear nth order differential equations from way back, you know, not these, but from way back, and say L of y is equal to 0. That would be the homogeneous case or homogeneous case, and L of y is equal to g of x. That would be your non-homogeneous case. Okay. Now, here's another principle, and this works with homogeneous equations. Okay? It's called the superposition principle. Okay? I guess I'll write that down. Yuck. Okay, superposition principle, really ugly writing. All right. We're going to start off with this. Let or understand that y1, y2, y3, ... all the way up to y sub k are solutions of a differential of a homogeneous nth order can't write differential equation, DE will satisfy that, on some interval I. Okay. If that's the case, if each one of those is a solution for some homogeneous nth order differential equation on some interval I, then automatically y is equal to C1 y1 plus C2 y2 plus C3 y3 plus dot 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 plus up to c sub k. I can't write. C sub k y sub k. Okay. This is also, okay, where your C sub i's, anytime I is equal to 1, 2, 3, dot, 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 up to k, are arbitrary constants. Okay. If that's the case, then this y is a combination of those. Y is also a solution. Okay. What it means, if you have a number of solutions, it doesn't have to be a huge number, just any number of solutions, then not only are those individually solutions, but any linear combination of those is also a solution. Any linear. Whatever your C sub i's are, where I is counted from 1 to k, as long as those are arbitrary constants, okay? We're having trouble reading or writing that. Then y is also a solution, okay? So, that's the super.
You could have an infinite amount.
What's that?
You could have an infinite number of solutions.
Yeah, yeah. And, but the thing is, it's not infinite. There is some finite k. And so you have that, but, oh, well, you sort of do, yeah. Because then when you include these being any arbitrary constants, yeah, you can put different constants in there and there'll be different solutions. Do I want to quite say it that way? There will be constants that will be a solution. I'll put it that way. I don't mean to say you can put any one in there. Well, yeah, I think it does say that. So, yeah, in that sense, there will be an infinite number of solutions because the C's could vary. Yeah. They're any arbitrary constant. You're absolutely right. Okay. Now, there's two corollaries to this theorem. A constant multiple C1 okay, of a solution of a homogeneous linear differential equation is also a solution. A constant multiple of a solution, that's a pretty ugly solution, y1 of x of a homogeneous linear differential equations. These are, remember, linear differential equations, is also a solution.
That makes sense.
Second?
That makes sense.
Yeah, right. Because it's any constant multiple, okay? And then the B one is a homogeneous or homogeneous, okay, linear differential equation always possesses the trivial solution. Okay. Now, remember though, we're talking about, I haven't written there anymore, homogeneous equation, okay? Homogeneous differential equation, where all that mass, all that mass, all that mass, all that mass is equal to 0. Well, if that's the case, y is equal to 0. This one is going to be 0. The first root of 0 is 0. The second root of 0 is 0. All those are, so yeah. It doesn't matter what your c's are there, that's going to be a solution. So that for a homogeneous linear differential equation, always has at least one solution, the trivial solution. Y is equal to 0. Okay.
Well, they're stating the obvious on these, aren't they?
Yeah, that one definitely is. Okay. Now, let's do example 1.4. How are we doing on time? Got about 15 minutes or more. Okay. So example 4. Here's a function. y1 is equal to x squared. And here's another function. y2 is equal to x squared log x. Okay? And these are both solutions of a homogeneous linear equation. They don't say differential equation, they just say equation, but that's fine. X cubed y triple prime minus 2x y prime plus 4y is equal to 0. Okay. That's a homogeneous linear equation because the derivatives only show up one in each term. No cross terms in there, no squares or powers of any nature, okay, except first power, and the whole thing's equal to 0. It's a homogeneous, linear, third order differential equation. Third order differential equation. Okay. Now, that's on the interval 0 to infinity. Now, one reason, you can't look at this and say, you know that's why it's true, but looking at your solutions there, x1, y1 and y2, that you said is a solution, for y2 to work, x can't be 0 and it can't be negative, because you can't take the log of 0 or a negative number. Okay? So that wasn't a priori, but looking at the whole picture, it has to be. Okay.
Wait, say that again now. Y cannot be 0.
Okay. Nothing here suggests there's any problem with the 0 or infinity, so to speak.
Right.
Okay. But now this is the interval on x. Okay. But if you look up here for these to be your solutions, no problem there either. Right? For the first one. But there's a big problem here. Because you can't take the log of 0 and you can't take the log of a negative number. You take the log of any positive number. So if this is a solution, it better be limited to that domain of x. Okay. Now, by superposition principle, the linear combination of y is equal to c1 x squared plus c2 x squared log x, okay, it says is also a solution to the equation on that interval. Okay? Now, let's do the math, I guess you'd say. let's take y prime, and that's equal to, this is your y, that would be 2c1x, right? Okay, plus c2, okay. Now this is a product rule here, right? Yes, we love them. Okay. How do we do the product rule?
The derivative of the first.
Okay, derivative of the first will be,
The second.
huh?
Derivative of the first times the
Okay,
second.
so that would be 2c2x log x plus, see, I just did derivative of this. So this is only have one.
Okay.
That's it.
All right.
So this is the product rule. Okay. So I'm just pairing the C2 with that. I can just pull the C2 out and just do it that way. It doesn't matter. So this will be 2C2x, that's the derivative of the first, times the second, plus, what's the next part?
C2x.
Yes, the first times the derivative of the second, right? So that would be plus C2x squared, that's the first, times the derivative of the second. What's the derivative of log x?
1 over x.
1 over x. So do a 1 over x here, and that wipes out that. Okay? So, I don't know, that's okay, leave it like that. Let's do our y double prime. Even though we don't need it in the equation up there, you still got to have it to do the y triple prime. Okay, so that'll be 2c1 plus 2c2 x.
Right, because.
Okay, so you're doing the first times the derivative of the second?
Oh, wait. All right.
Doesn't matter.
You're right. The derivative of the, what is the derivative of the first of that one? That one, that's going to be, yeah, 2c2.
Just C2. The derivative, if this is your first function, then the derivative of that is just 2c2 without the x. But I thought maybe you're doing the first times the derivative of the second, whichever.
Well, let's do the first.
The first times the derivative of the second?
Yeah.
Okay, so that times 1 over x.
That's just going to be.
So that goes away. Okay? Plus.
Hang on. The first of it is C2.
This is just the derivative of that is C2. 2C1.
Right.
Derivative of this, okay, are you doing the derivative of this or the function of that? Is this the derivative or is
the function
u v prime plus v prime u or v prime u plus u v prime? I mean, it doesn't really matter which order. You want to do the function first, this function first, or you want to do its derivative first? You got to do them both. Doesn't matter which one.
That's fine, whichever one.
Okay.
Whichever one.
Okay, well, I thought you said this. So we're going to do this one times the derivative of this, which is 1 over x, which those go out. Then you got to go back and do the derivative of this one, which is a 2c2, right? Log x, right? Derivative of the first times the second. Okay. Just this term here, taking its derivative, right? It's the first times the derivative of the second, which is that one, plus the second, and plus the derivative of the first, 2c2, times the second.
Why is 2c2 the derivative
of 2c2x? Because this is the first power.
You're right.
Yeah. Okay. And then we still got the last term, which is just a c2x, so that's just going to be plus c2. Derivative of that is just, oops, I put it in the wrong line. Sorry. On my old program, I could have just drug it back down where it belonged. I can't do that here. Plus c2. Okay. Well, we can simplify that a little bit, and that will be this. 2c1 plus 3c2 plus 2c2 log x. All right. Okay.
Oh, I'm sorry, I'm looking at the wrong line. Okay.
Yeah. It's this plus that, plus that, plus this. Well, these two are the same.
Mm-hmm.
I mean, same like terms. So that would be 3c2. Right. And then plus that.
Yeah, like I said, I was looking at the line above it, and it wasn't making any sense.
All right. All right. So let's do the third derivative, which is the derivative of the second derivative. Well, guess what? Derivative of 2c1 is 0, because that's a constant. Derivative of 3c2 is 0, because that's a constant. And this other one is just 2c2 over x. There's your third derivative. Okay. All right. Now, so there's your that. Now, if we multiply that by x cubed, like the top one says to do, that's going to be 2c2 x squared, right? Because this x cancels out the x cubed. Okay? So this would be 2c2 x squared. Okay? Minus 2x times y prime. Well, here's your y prime. So let me back off a moment on that. Okay. The minus is going to change all the signs in this. So it's 2x times 2c1x. That would be a minus 4c1x squared. That's the first term. Minus, because all these are plus signs here, plus 2 times 2 is 4 again, c2, again, this time c2, and we have an x times x is x squared, and then a log x. Okay, minus, okay, wait, I'm still doing this one more term here, minus 2 from here, x squared. Okay, 2x times minus 2x is minus 2x. c2x, I left off the c2. I knew I was leaving off something. Minus 2c2 x squared. Okay, that's minus 2x times y prime. We got that one there. Okay, plus 4. Whoops, wrong line. I've done that twice. Quit. At least twice today. Started adding on the wrong line. Plus 4 times y. Well, that's 4c1 x squared plus 4c2 x squared log x.
Is that minus 2c2x squared? Yes.
Right here. Yeah, oh, this one right here. Yeah.
Yeah,
Minus 2c2 x squared. Yeah, I left off the c2 when I was writing down. Okay. Now, let's see what we got. Here's we got a 2c2 x squared. . and here we have a minus 2c2x squared. First term and the fourth term. Here we have a minus 4c1, I think that's the one, yeah, x squared, and here we have a plus 4c1 x squared. Okay, here we have a minus 4c2 x squared log x. Here we have a plus 4c2 x squared log x. Sure enough, that's equal to 0. Okay, because a linear combination of those, since those produce our solutions, any linear combination of them is just going to combine those separately but added together, okay? And so you're going to wind up with still equals 0. That's just an illustration of the superposition principle. Okay. Now, I think I've got to end it there because I think we're just about out of time. So throw your expensive calculators around. Oh, glasses, huh?
We got like 2 minutes.
2 minutes. Okay, well, let me just mark this place here. We'll start with linear dependence and linear independence for next time. Okay, and let's see if we got enough to do any homework exercises. This is a long section. I think you can do either 1 or 3. We've done theorem 4.1.1, haven't we? Because we're in 4.2 point something now, aren't we? 4.1.2. Yeah, you can do, I think, number 5, especially if it's in the back of the book. Okay? Let's just hold off there. Just do those. That'll be enough. Okay. And you've got your second test to be working on, and research paper, yeah, that to be working on.
Yes, I keep forgetting about it.
So that's enough to make your spring break memorable. Okay.
Oh, God, we got spring break next week.
Yeah, spring break is next week. Oh, you weren't here. Yeah, that's right. You weren't here last time. I made the announcements. I would have made the announcement, but nobody was in here, so I didn't. It's a good news, bad news situation. Good news, next week is spring break. The bad news, we won't be meeting. Okay, so get over it. All right, now the other announcement that I had said, I don't know if you're at all interested. Yesterday, they sent us this Monday, before class Monday. I didn't get it until after class Monday because I had to check my boxes earlier that morning. There is 2 new buildings on the Birmingham campuses. One on Birmingham West campus, this new Academic Success Center. It's where the old either Winona Elementary or Middle School was, that closest to the West Boston campus. They tore that down and built this instead. An enormous building. I don't know what all they're going to put in there. It's mostly for student services. There are 2 things I think someone told me that could be used as classrooms. So I hope we'll be able to use at least 2 rooms as classrooms. That's on Wilson Road, just barely on Birmingham West campus. Then across Wilson Road on Birmingham East campus, there's a new dorm. It's not dorm, residence hall 2. And this is right next to the previous residence hall 1. It's also a fairly new building, but this is just now completed. And they had the grand opening yesterday. So I didn't get to go because I was teaching, but I might go by there tomorrow just to take a look. But anyway, just to let you know, so you would be in the dark about that. Okay. Good deal. We will see you in
2 weeks.
Yeah. A little less than 2 weeks. I'll see you on Monday of 2 weeks from now. Yeah. Good deal.